Strategies for integration. Objectives. By the end of this lesson, you should be able to determine which strategy to use when solving an integral. So here's the general strategy for solving integrals. The first thing we have to decide is if the integrand has a general antiderivative. So we want to think about it in this order. We look at the integrand and ask ourselves, is there something we know of such that when we take its derivative, we get that out as the answer? So that really means knowing your derivatives backwards and forwards. So if there is no general antiderivative, then the next thing we would try to do is apply some algebra, some algebraic manipulation, like distributing or simplifying a rational function if possible, if there's one term on the bottom. But that may not be possible. But if it is, we simplify and use general antiderivative rules. If it's not possible, then our only strategy at that point is to try U-substitution. So this may include recognizing when the solution involved is a transcendental function. So there are other strategies for solving integrals, or there are other methods besides U-substitution. So if you're in BC calculus, that is integration by parts, or the method of partial fraction decomposition. But for us, if it's not one that has a general antiderivative, or we can't do any algebra to it to make it a sum or difference of a bunch of things with general antiderivatives, then all we have is U-substitution, right? So we got to figure out our U and a way to make that work. So the other thing I want to remind you of is when solving an indefinite integral, you should be able to take the derivative of your answer and get the original integrand if you're right. And I can't stress enough that that is just great practice, going backwards and forwards, because it's going to involve the chain rule, and it's just going to be great practice all around. For the following problems, decide whether the integrand has a general antiderivative, which I'm going to abbreviate as GA. If we need to do some algebra first and then find a general antiderivative, I abbreviate that AGA, or if U-substitution or U-sub is needed. If U-substitution is needed, we're going to find the U. So I put the asterisk. By algebra, what I mean is performing some operations on the variable x, not just pulling out a number or rewriting an exponent. So that's what I consider to be that algebra first. And you'll see what I mean as we go through these problems. So by the end of this, I really want you to try to have a good feel for looking at a problem and going through those steps in order. So we're going to kind of take these in sets of either 2 or 4. So we're going to start with analyzing these first 4 functions. So we'll look at the first one. We start by looking at the integrand, right? So we're looking at x times x squared plus 3. And the first thing we're going to ask ourselves is there a general antiderivative? And the answer to that is no. So I don't have a sum or difference of a bunch of terms. So I have this product, and I don't know something such that when I take its derivative, I get this specific thing out as its answer. So the next question I'm going to ask myself is there any algebra that I can do so that I can just use my general antiderivative rules? And the answer to that is yes. I can distribute in this x variable so that this becomes the integral of x cubed plus 3x dx. And now, since these two things are being added or subtracted, I can apply the power rule to each one. So I would consider this AGA. Now, the important thing isn't really necessarily getting this piece right. The important thing is solving the integral correctly, right? But I'm just trying to give you a way to think about how to go through and solve this. So the next problem is slightly different. So I'm looking at this one. I have x times x squared plus 1 to the 4th. So again, always start with that process. Can you find a general antiderivative? Can you go straight from this to an answer? No. Then the next question is, can I do some algebra? Well, because this exponent of 4 is here, I cannot distribute this x in, right? Order of operations, I have to handle exponents first. So it's like I'd have to multiply x squared plus 1 times itself 4 times first before I multiplied in that x. So that's not really worth it. So instead, on this one, we're going to do a U substitution, right? That's all that's left if I can't do any algebra. And my U is what's on the inside. So most of the time we're looking for that inside piece or that denominator, and this one follows that rule. So we have x squared plus 1. And then what I'm ideally looking for in a good U is that du, which in this case is 2x dx, is that looks a lot like what's left over. So remember, this piece is going to become my u to the fourth, right? That didn't go away. And I need to replace x dx. Well, I got out something close. So x dx is a half du. So now my integral is going to become 1/2 the integral of u to the fourth du. So u substitution is the way to go. Now, does that mean on this problem I couldn't use u substitution? No, it doesn't. I could have done u substitution here, but that was not the most efficient method. So here it would have been easier to distribute as we did with algebra and then do a general antiderivative of each piece with the power rule on each of these. Now looking closely at the next two, they're very similar as well. So I have 2x minus 1 squared and 2x minus 1 to the 7th. Now, on the one on the left, again, I'm going to use AGA. That is the better strategy. The algebra that I'm going to do is 2x minus 1 times 2x minus 1. I only have to do it twice. So that requires me to just distribute out. So 4x squared minus 2x, so minus 4x plus 1. And then now I'm doing the power rule on each piece. So that would be the better strategy here, I would say, as opposed to on this one, it would not be a good idea to use algebra because now you're multiplying this thing out 7 times. So instead, we use u substitution. Du is 2x minus 1, du is 2 dx. I only want a dx, so I'm going to divide both sides by 2. So a half du is dx. So this integral becomes, so this piece gets replaced by u, so u to the 7th, dx, right? Dx gets replaced by a half du, so we stick that half in the front, and now this is what we're integrating, which is nice. I can use the power rule. So this one requires, quote unquote, requires a u sub. So in the sense that, yeah, you could do all this algebra, but nobody really wants to do that, right? So we can see they're just so slightly different, but there's a better strategy to use on these two on the left, which is that algebra first. Let's go ahead and scroll down and look at the next couple problems. Again, we'll look at this group of 4 together here. So I have the integral of x squared plus 9 over x, and here I have the integral of dx over x squared plus 9. And then I have the integral of x over x squared plus 9 dx, and the integral of x over x squared plus 9 squared dx. So if you're overwhelmed by looking at these 4 problems next to each other, I don't blame you. So that's why we're going over a strategy. So let's take a look at this first one, right, one at a time. First question, is there a general antiderivative? Can I go straight from something that looks like x squared plus 9 over x and tell you the derivative of blank equals this thing, this integrand? No, there is no general antiderivative. But the next thing I try is algebra, and that algebra is recognizing that there is only one term on the bottom, so that this is x squared over x plus 9 over x, which is the integral of x plus 9 over x, which now I can do each one separately because they're being added together. So this only works because I'm able to go I'm able to divide when there's only one thing on the bottom. I can split it up. It does not work the other way around, like the one below it. I cannot split this one up. So we'll get to that one. But this one, I can just go to now x squared over 2 plus this one. The 9 comes to the front. This is like 9 times 1 over x, whose antiderivative is ln x plus c. So AGA is the strategy, that algebra first, because there was one term on the bottom that I could split up into a sum or difference of now pieces that I can integrate separately with general antiderivative rules. Now looking at this one, so it's pretty unique. So I have dx over x squared plus 9, and the ideal situation is that you automatically recognize that the answer is a inverse trig function. The answer is going to involve arctangent. Now let's just assume you didn't know that. Let's try to work our way to that process. Now, first things first, is there a general antiderivative? So the answer there is yes, there is. But again, what if we didn't recognize that? Is there any algebra we could do? So this is like 1 over x squared plus 9? No, I cannot split this up. There's one thing on the bottom, two things on the top being added or subtracted. There's nothing I can do to that. Let's say you tried U-substitution. So I want to do the wrong strategy. That is wrong. But I want to just get stuck because I want you to see what it's like to get stuck so you stop and don't try to force it. So if you try to let u be the denominator, then du is 2x dx. I don't have any other x's, right? So I would essentially be replacing, I would divide both sides by 2x so that dx is du over 2x, and my integral would become the integral of du over 2x, because again I'm replacing dx with du over 2x over u. That is a whole lot of wrong. I cannot have x's and u's in the same integral. That's not the point of U-substitution, which is a change of variable completely. No x's. That's a problem. So this was not the right strategy. So that's when hopefully you go back and rethink, well, what does this look like? What form does it take on? And it takes on the form 1 over x squared plus 3 squared dx, which then hopefully you do realize does have a general antiderivative, arctangent. Now, arctangent's formula is 1 over a arctan of x over a. So this is general antiderivative. Sometimes I say general antiderivative t for transcendental, but ultimately it's just we go straight to an answer. It's just that you had to recognize it. But if you didn't recognize it, well, you can't do any algebra, and u sub gets you stuck. So that means we had to go back and rack our brain for that formula that we need to have memorized involving arctan. Now these next two, I have x over x squared plus 9, so it's the reciprocal of this one, and x over x squared plus 9 squared. Now both of these problems require U-substitution. So there's no general antiderivative if I look at each integrand. And so I am going to try to let u be the denominator, right? That one's usually the one we try first, and it's going to work out because du is 2x dx, and I have an x dx, so it's all going to work out here. And then over here, same thing, u is x squared plus 9 again, not x squared plus 9 squared. So I just want to show you what happens if you do that. If you let u be the whole bottom, the problem with that is the derivative of this requires a chain rule. It's 2x squared plus 9 to the 1 times 2x. And again, you get totally stuck. There's no x squared plus 9 on the top, right? There's just an x on the top. So that was the wrong strategy, right? Let's just erase all of that. So my u is just x squared plus 9. And then du, again, is 2x dx, and I have an x dx, so it's going to work out. So u is x squared plus 9 in both of these cases. Now, on this one, I'm going to end up with 1/2 the integral of 1 over, or du over u squared, which I just want to remind everybody is not 1/2 ln of u squared. Please, please don't do that. So it would need to be 1 over u. This one is going to turn into 1/2 the integral of du over just u. So this one is going to be natural log of u, and then plug the c back in. This one, what do we have to do? We have to rewrite it as u to the negative 2. So again, that's review, but I can't help it. I don't want to see that mistake. Alright, so now let's look at the next set of problems. And here we're looking at the integral of x e to the x squared plus 1. And on this one, we have cosine over e to the sine x. So both of them involve e. And the pattern that I want you to see is that, first of all, no general antiderivative. I have no idea what I could possibly do to take the derivative of and get this out as an answer automatically. And there's no algebra, right? There's not a whole lot of algebra I can do, or in that case, since I have trig functions, there's no little trig manipulation. So I'm stuck with U-substitution. And on both of these problems, u is going to be what's on the inside of the exponential function. So e to the x squared plus 1, x squared plus 1 is on the inside of e. So u is x squared plus 1, then du is 2x dx, and I have an x dx. So I get 1/2 du is x dx. So 1/2 e to the u is what I'm going to find the antiderivative of. Here, same thing. U is going to be what's on the inside of e to the x. So that is sine x. Now, sometimes people incorrectly choose the entire bottom, and that means that you don't really want to think about it. I mean, so it's often what's on the inside or what's on the bottom, but it's really what can you find as an inside or a bottom of some kind, such that when you take its derivative, or it may not even be on the inside or on the bottom, really, what function can you choose such that when you take its derivative, it's somewhere else in the problem? So du is cosine x dx, and I have a cosine x. Whoops, this is missing the differential. I have a cosine x dx. If you let u be e to the sine x, the whole bottom, then du is e to the sine x times cosine x. It's the chain rule. It's the original function, e to the f of x times f prime of x. And we don't have an extra e to the sine x. So this is wrong. Don't even write it down. It's totally the wrong thing to do. U is what's on the inside of the exponential function. And now this becomes 1 over e to the u du, which is not natural log of absolute value of e to the u. Just again, the millionth reminder that this is not it. We'd have to instead rewrite it as e to the negative u, which would be negative e to the negative u plus e, and so on. But it's not ln of e to the u. Alright, let's take a look at these next two problems. I have natural log x, quantity squared over x, and here I have sine inverse of x over the square root of 1 minus x squared. So I put these two problems sort of next to each other on purpose, and even in this group of 4 on purpose, because they all kind of break that rule. So that rule of, oh, it's always the inside, or it's always the whole denominator, like that's often true but not always. In this case, my u, because ln x is anywhere in the integrand, u is just ln x. And then du is 1 over x dx. So now that 1 over x dx is really in this problem if you think about writing this as 1 over x ln x quantity squared dx. Right? This is another way to write this because it's multiplicative. So this is like ln x squared over 1. And when you multiply fractions, right, I'm using this property, a over b times c over d is ac over bd. I just multiply fractions straight across, right? So that's the property that I'm using. I'm just going the backwards direction. Whoops. So now, hopefully I can see that substitution, 1 over x dx is du, and then ln x is u squared. So this becomes u squared du. And then I would just take the antiderivative. One of the things that I want to mention, though, is when I show how to split it up like this, you cannot do each one separately. So that's like another huge problem. And why can't I do each one separately? Because they're being multiplied, right? Only if things are being added or subtracted can I do each one separately. So the only reason we split it up like this is to see it better. So that ties into this next one. The u that we're going to choose breaks the mold of being on the inside or even on the bottom, because the u we're going to choose is sine inverse of x, because du is 1 over radical 1 minus x squared dx. And again, if you can't see that's here, that's because we can rewrite it as this, that whole splitting it up as a product, what we just did right over here. I can split it up as a product. Again, I cannot do each one separately, but I'm rewriting it so that I can see that sine inverse of x is u, and 1 over radical 1 minus x squared is du, right? That's this piece. So now I'm just integrating u du. So that, again, comes with practice and knowing your derivatives backwards and forwards. If you would have known right off the bat that the derivative of sine inverse, or arcsine, is 1 over 1 minus x squared, then you could see a little more clearly what you should choose as your u. Now, if you didn't, and you try to let u incorrectly be 1 minus x squared, you're going to get all kinds of stuck. You're going to get negative 2x dx. I don't have a negative 2x dx. Right, I have sine inverse of x, which is like stuck together, so I can't do anything weird with just this x. That doesn't make any sense. So I would get stuck is the bottom line. Alright, let's keep going. Let's look at the next couple problems. So here I have x squared plus the square root. Whoops, I just realized something. I'm sorry about that. I did not even go over the strategy. We wrote it down, but we didn't do it. These are all U-sub. Sorry. These were all U-substitution. Right, so no general antiderivatives and no algebra that we could perform. Alright, so now looking at these next couple problems, I have x squared plus the square root of x cubed minus 2 over x cubed. Now this one, every single piece is being added or subtracted, so I can take the general antiderivative of each one separately. So the only thing I want to go over about this problem is how to rewrite each piece so that I can apply the power rule. This right here becomes x to the 3 over 2. I don't exactly know what's happening, but a lot of people somehow keep taking this and making it x to the 1/3 when it's not. This is x cubed to the 1/2, right? Square roots, there's like a secret 2 right here, and it's the square root becomes a power of 1 over 2. So that's where the x to the 3 over 2 comes from. We multiply these together. And then this becomes negative 2. The 2 comes to the front because this is like 2 times 1 over x cubed. And now this is x to the negative 3. So this is 2x to the negative 3. And I'm really taking the time to go over this because they're being missed a lot. I know you know the power rule. If I were to have just given you x to the 3 over 2, you're going to do it correctly. But it's that rewriting the exponent, or even this, somehow the 2 goes to the bottom for some people too, and I'm not sure where that's coming from. So this is how I'd have to rewrite it, and then I'd have to apply the power rule. Alright, looking at this next one, I have sine 2x plus cosine 2x dx. Now the key to this one is that they're being added together. So since they're being added together, I can do each one separately. And each one has a general antiderivative. So this is GA. So this has a formula, right? Because this is like sine of kx plus b. So this is 1 over 2 negative 1 over 2 cosine of 2x. And then this one is plus 1 over 2 sine 2x plus c. And that's it. I went straight to an answer, right? As long as I knew the formula for each one and realized I can do each one separately, that's it. It's a general antiderivative. But for whatever reason, I've had some people just get all kinds of lost and try to do U substitutions on this. And they try to say, okay, we'll let U be, sine 2x, and then du is 2 cosine 2x. That's not wrong. It's not wrong at all, dx. But then here's the big problem. They end up getting u plus du. This is not a thing that makes any sense. So I cannot have u plus du. This differential cannot be added. This just doesn't really make any sense at all. So the big picture is that when things are being added or subtracted, we do each one separately, just like derivatives. So don't get lost in U substitution and trying to use it for absolutely everything. In fact, we pretty much try to avoid it, right? We try to do general antiderivatives first, and then we try algebra to avoid it. So it's really that last case scenario. On this one, I have x squared minus 1 times x minus 1. Here, general antiderivative, no, because not everything is being added or subtracted. I have this product. But I can do some algebra first. So AGA, this is going to be x cubed if I distribute, minus x squared minus x plus 1. And now, since every term is being added or subtracted, I can take the antiderivative of each one separately. So that's going to be the strategy on this problem. Algebra first, right? No U substitution. I think people start to see insides and want to do U sub, but it's just a straight, distribute out, take the power rule of each one. The next one, I have the integral of tangent x dx. And on this one, a lot of people want to say secant squared x, in which case you'd be taking the derivative, right? The derivative of tan x is secant squared x. And what follows from that is that the integral of secant squared x is tangent x, but it does not mean that the integral of tangent x is secant squared x. So what we have to do is know a little bit of trig. So this is almost like a t in front of U-substitution, because first I have to do some trig rewriting and know that this is sine x over cosine x. And now I have to use U-substitution, where u is the bottom, cosine x, and then du is negative sine x dx, and it's all going to work out from here with my u sub. But in order to do that, I had to rewrite tan as sine over cosine. So this is just a side note. I mean, it's just a very common mistake on this type of problem, is that forward and backward understanding of derivatives and antiderivatives. And now let's go ahead and take a look at the last couple problems. Alright, we have the integral of 3x squared times cosine of x cubed, and then we have 3 cosine of 2 plus 3x dx. Alright, so this one, no general antiderivative. There's no algebra I can do, so I'm stuck with U-substitution, and my u is going to be the inside of cosine, x cubed, and we know it's a good u because du is exactly what's left over outside of cosine. It's 3x squared dx. So 3x squared dx is du. And then we're going to replace x cubed with u. And I can't forget the cosine. A lot of people keep doing that, forgetting that trig function if you picked the inside. So cosine u to u, now we integrate that and then plug u back in. So this one is u sub. Now this next one, 3 cosine of 2 plus 3x, can be solved with U-substitution. I would not recommend it. I would say this is a general antiderivative. This is of the form cosine kx plus b, except we just have to do a little rewriting, right? Kx plus b. So the antiderivative is going to be 1/3 sine of kx plus b, but I can't forget this constant here, 3. So those actually cancel, and it's just sine of 3x plus 2 plus c. And we can go straight to an answer. Now, U-substitution would have worked. U would have been 2 plus 3x, and then du is 3dx. So absolutely, it would have worked. But I really want you to try to identify when I can go straight to an answer, because it's a time saver. And you really have to be good with identifying the best strategy, best quote unquote, that moves you along quicker so that you have time for some of the more challenging questions. And now the last two on here, we have the integral of cosecant x cotangent x dx, and then ever so slightly different, the integral of cosecant squared x cotangent x dx. Alright, so this one here, it's either you know it or you don't. It is a general antiderivative, because there is something that I know of that I can take the derivative of and get cosecant cotangent, or close to it. It's negative cosecant x plus c. The derivative of cosecant x is negative cosecant cotangent, so I'm going to have to throw in an extra minus to cancel out with that negative. So this is the answer. We can go straight to an answer. So it's a general antiderivative. And then this last one does not have a general antiderivative. There's no real algebra I can do here, so it's a U-substitution. And the u that I would choose here is cotangent x, because the derivative, I should know the derivative is negative cosecant squared x dx. So that's close to what I have left over as long as I divide out the u. So now this would become negative the integral of u du. So it's a lot easier to solve by taking the antiderivative and then plugging cotangent back in, right? So it's going to be negative u squared over 2 plus c, and then plug in cotangent again. Cotangent x, right? Trig functions make no sense without their variables. So this would be my answer. So this one does require a u substitution. Now, I mean, ultimately, there's hundreds of problems that I can go over, but the idea was to develop the strategy behind solving this. The other thing I'll have you recognize is that all of these were indefinite integrals. They didn't have any numerical values, but that doesn't change really what we're trying to do. So let's just say I made this 0 to pi, I'm just making up numbers here, of cosecant x, cotangent x dx. What this is telling me to do is find the antiderivative, which I just did, so negative cosecant x, and then plug in pi and plug in 0. I'm not sure how this is going to work out. I'm not even going to solve it all the way. But that's the only difference between what these limits of integration do. It makes it a definite integral. It makes our answer a number. But it doesn't change the fact that I have to find a general antiderivative first, right? I have to get to here and then plug in the numbers. I never just plug in the numbers. And when I have to do a U-substitution with values here, that makes it a little trickier, right? I have to change those numbers into U values before I can treat them as values that go in after taking the general antiderivative. The only other thing I want to just share is that, the one type of problem that we didn't go over here, it's a U-substitution, but one that involves a transcendental integral. So if I had something like dx over 9 plus, I don't know, 16x squared. This is of the form dx over 3 squared plus quantity 4x squared. And this one's going to end up being an arctangent, but it needs a U substitution of U is equal to 4x, so that I can turn this into just a single variable squared. So this is like a subtlety, but it's, again, a U substitution. It's about knowing those general antiderivatives. So I mean, we can't go over every single type of problem so much as it's that practice, it's that repetition, and it will get better over time.